So we were talking about the expansion of the universe. We talked about how as the universe expands, the forces tend to separate out. So the Planck error, we can't really describe what happens in the first 10 to the minus 43 seconds. We do know at the very end of the Planck error, there's something called a spontaneous symmetry breaking, creates gravity as a separate force. This spontaneous symmetry breaking also has the potential of creating a slight anisotropy in the universe, which would then cause later, when particles start to form, a slight imbalance between particles and antiparticles. Okay. After the 10 to the minus 43 seconds, though, gravity is a separate force. And we have gravity and the grand unified force. And so theorists try to explain how this grand unified force works, and there's several, they call them guts or grand unified theories. And so the different ones are slightly different and have slightly different predictions, which particle physicists are in fact eagerly testing right now in some of the biggest high energy physics machines in the world, such as at Fermilab and more particularly at the Large Hadron Collider in Europe. They were going to build something here in Texas, the superconducting super collider, that was really designed to test these grand unified theories to really figure out how these forces all sync together and how the structure of the universe really is established. And so again, as Congress was debating whether or not to fund it, the particle physicists said that they were trying to recreate the Big Bang, and that really didn't go over because people thought they were going to blow up the universe. And so they weren't trying to blow up the universe; they were just trying to create a spot in the universe with so much energy that you created a slight, tiny little area that allowed you to figure out what was going on after the Big Bang. One of the things that you do notice, though, is that because you don't have a separate strong and weak force, that the elementary particles are completely indistinguishable. You cannot tell the difference between a muon, meson, tauon, lepton, baryon. Nothing was distinguishable from anything else, and so everything was just alike. And so as you start creating particles, normally E equals mc squared, you get equal particles and antiparticles. And again, we have the spontaneous symmetry breaking, which could possibly have created a tiny bit more in the way of particles than antiparticles. And that means that for every 10 billion antiparticles, you get 10 billion and 1 particles. Well, if an antiparticle and a particle meet, they annihilate each other to release energy. And so these things are all close together, so they'll start running into each other, which would mean that when you're done, you would have left over slightly more matter than antimatter. And so that's one of the consequences of the grand unified theory. Well, an interesting thing. When you're talking about these forces separating, physicists talk to as forces freezing out of the universe. And the reason we use that term is mathematically, the forces separating out actually operate much like a phase change, like water turning from liquid to solid. And so that phase change is kind of what's going on here. Well, that creates an interesting sort of thing. Everybody knows what temperature water freezes at, right? So I ask people what temperatures water freezes at, and I say 32 degrees. And I say, so does that mean that at 31 degrees all water is solid? Well, no. You can have water at 31 degrees that's not solid. Well, wait, how can you do that? Well, one way of doing it is to keep the water moving. So moving water can actually cool below 32 degrees Fahrenheit. You just don't allow the molecules to arrange themselves so that they become solid. Well, that's an interesting sort of thing. That means now what you have is cooled water. So, and of course that's the idea of why in the wintertime you'd leave the faucets dripping a little bit, so the temperatures are going to drop below freezing. The circulating the water keeps it from freezing. Likewise, if you have a swimming pool, let the pool pump run. The circulating water would keep the water from freezing. Okay. So that's one of the things. The other thing, though, that surprises people is the other way of keeping it from freezing is don't bother it at all. If water is kept entirely, completely inert, in other words, you're not vibrating it, not moving it, not disturbing it, you cool the water. What can happen is you can sometimes cool it past the point at which it would freeze. We call this supercooled water. I remember as an undergraduate, we did this in lab. We'd take a beaker of water and very, very gently cool it to just below freezing. And if you do it just right, you can actually cool it below freezing without it freezing. But if you thunk the edge of the water, you have this wave of freezing that ripples across the water. And so the possibility exists that the universe could actually supercool past the phase transition. Now, when you thunk the water, and you can actually see videos of this sort of thing being done on YouTube. So just look up supercooled water, and so you disturb it, and it just suddenly freezes. When it freezes, it gives up the energy that was in the liquid phase as it becomes solid, and it actually warms up. So if the universe gives up this energy, well, it's not so much energy, but it's something like energy, goes into the dark energy. And what that would do is that would actually go into space itself. You can't really warm the space, so what you do is you expand it. So if you supercool past a phase transition, in other words, if the strong force is supposed to freeze out, but you don't freeze it out right away, expand a little bit too much, then if some disturbance causes it to start freezing, then it separates out as a wave across the universe. And when it does, that energy goes into the universe, causing the universe to expand. When it expands, then it will expand vastly. This is what we call now. This was worked out by two physicists, Alan Guth and Andre Linde, separately from one another. And when they calculated it, it realized that space itself would expand. Well, how much expanding? In about 10 to the minus 32 seconds, the universe would expand by a factor of 10 to the 50. 10 to the 50 is enormous. What does that mean? It means if you had a hydrogen atom, it would suddenly have, in a fraction of a second, a diameter of 10 to the 24 light years. That's bigger than the current universe. So a single hydrogen atom would suddenly expand bigger than the universe is today. And that expansion rate is like 10 to the 63 times the speed of light. That's startling. But wait, didn't we just say nothing can expand faster than light? And yet the universe would seem to. How does that? Well, it does not violate relativity, because nothing is moving faster than light. Literally, nothing is moving. Empty space is expanding. Things are going along for a ride, but they're not moving. They're sitting still and getting farther apart because space is stretching. It's like, standing on a conveyor belt or an escalator. You stand on an escalator, you're not walking, but you're still changing where you are. You're just going for the ride without moving. Something's moving you. Okay. But if you look at where you are on the escalator, the step on the escalator, you look down and you're not moving because the escalator's moving. So space is the same way. Galaxies are not moving away from each other. They're sitting still. Space is expanding. Space-time is not a thing. Therefore, it can expand. So relativity says things cannot move through space faster than light. It does not say that space cannot expand. And everything just goes along for the ride. Well, thing is, that solves the flatness problem. When you walk out, we know the Earth is spherical, but when we walk out and look at the Earth, it looks flat. Why does the ground look flat? Well, it looks flat because we are so close to it. So if you were to take a sphere and expand it vastly, it would look flat. That's why the universe would look flat. It would keep expanding until it basically flattened out. Maybe that's what stopped inflation. Maybe that's what stopped it. Maybe that's what stopped the expansion, was the universe flattening out. This could also be another explanation for why the universe looks all the same. Because at one point, again, if the universe was expanding here, then what would happen is one side of the universe would look different than another side, because there would be not time to interact. But there's time for these little things to interact close together, then they all expand. And so everything we see in the universe was originally so close together it could interact with each other, which is why the universe looks the same in all directions, same temperature and so forth. And so that solves the horizon problem. So this inflation idea solves both the horizon problem and it can also separate matter and antimatter, and again, this is another possibility that would explain why the universe is all matter, not antimatter. So the universe would start off as a singularity, start expanding a little bit, and then you overshoot. Gravity freezes out, you overshoot, and then all of a sudden you expand drastically, and then you freeze out as you're freezing out the strong force, and then it expands from that point on, pretty much the way we've already talked about it. At that point, the gravitational waves stretching through the universe would then tend to create these density waves that gave these bits of light and dark that we see in the cosmic background radiation. They tried another experiment looking for inflation, the bicep telescopes and telescope, because what would happen is if this happened, then the universe should be polarized. The background radiation should be polarized. So you may read about this on the internet somewhere. So they looked for it. They announced they found polarization, but at first they announced that this was a confirmation of the cosmological constant. However, while they initially said they thought this was the cosmological constant, that rather the proof of the cosmological constant, proof of inflation, that we now think that they actually might have actually measured a variation or polarization within the interstellar medium near us. So that may have contaminated the data. So this is not necessarily proof of it. So we're still waiting on ironclad proof of inflation. Well, the thing is, this inflation sort of thing raises another interesting idea. If space can stretch, could it be possible you could intentionally stretch space? So Miguel Alcubierre, a Mexican astrophysicist, worked a number of years ago and came up with the mathematics that says, yes, if you could somehow distort space, so you squeeze space in front of a spacecraft, expand space in front of or behind a spacecraft would not move. It'd stay put, but the space in front would get smaller, space behind would get bigger, and you could actually travel faster than light. So this would be a way of traveling faster than light. Now the problem is it would take so much energy, it would not be feasible. So that's why it's a difficulty, but it's an interesting sort of thing. One other thing about this freezing of space, and that is if you freeze water, this wave of freezing sometimes doesn't line up just right, and you get a defect, a crack. A crack, for example, this is a semiconducting device put together and has a crack down the middle because of this topological discontinuity. That discontinuity could result in what we call a cosmic string. The cosmic string would be this like linear sort of discontinuity through the universe. And I'll pick up with that with our next lecture.